Hey everyone, so I did it. I've been thinking about this lecture for 3 years, probably maybe 2, and I put it together in a way that I think hopefully makes the most sense for how to approach SN1 and SN2 reactions in terms of under which conditions will which one be which. That's a lot of whiches, but alright, so please ignore if I don't have it subscripted. I'm sorry about that, but all right, so let's go ahead and briefly review these two reactions. So in an SN2 reaction, it's a one-step reaction, right? Happens in a single step. And in that single step, you're going to have some kind of substrate that's going to have a leaving group. So this is bromine is going to be the leaving group, and we should kind of have this down from other lectures already. This is just more to really condense it once you have a basic idea of how things work. So we have a leaving group here, and this is going to be our nucleophile. So this is a nucleophile, and the nucleophile has some kind of electron-dense area, oftentimes with a negative charge, but certainly if it's got a lone pair, it can do something. So this lone pair is going to attack that carbon. That electron that was, the electrons that were holding onto the bromine go onto the bromide now, and that's over here, and they join forces, and you get this final product here. Okay, in an SN1 reaction, the very first step, this is going to be a two-step reaction, kind of counterintuitive, but we talk about the reasons for that two-step step. I don't know why I wrote two-step step. That's a two-step reaction. Okay, and in this case, the leaving group leaves first, every single time. So we talk about stability a little bit, but the reason that it leaves is because it gives this wide open space with a positive charge there, you know, carbocation, and then the nucleophile can come in and attack that positive charge spot, and we get this as our product. Okay, so two different things. One happens in one single step, the other one, the leaving group leaves first, and then we have this. So how do you know when you have an alkyl halide or something with a leaving group, which one's going to occur? Well, there's a variety of factors, and we're going to go through those factors. The first factor is the electrophile itself. So that would be what I've been calling the substrate. So if it's a methyl or if it's a primary, it's pretty much going to go via SN2. If it's a secondary or tertiary, if it's a tertiary, it's going via SN1. But if it's a secondary, it can go either way. So really, the only time you guys have to freak out about anything, the only time you should consider other factors is if you have a secondary alkyl halide. The rest is already determined for you. So you can look at something and say, is it a methyl alkyl halide? Is it primary alkyl halide? Or is it a tertiary alkyl halide? If these are the answers, you already know which mechanism it's going to choose. So let's do a few examples real quick. So remember to find if something's primary, secondary, tertiary, etc., you find the carbon that the alkyl halide's attached to, and then you ask yourself, how many carbons is that attached to? This one, for example, has 2 that it's attached to. This is secondary. So this would be a situation where we're like, freak out time, okay? However, this next one, we have a bromine, and it's attached to this carbon here. And that carbon is only attached to 1 carbon. So this is primary. Primary will always occur, as we just discussed, via SN2. Then we have this next one. You follow the alkyl bromide to the carbon that it's attached to, and then ask how many carbons that thing is attached to. Here we have this one and that one. This is secondary. Freak out time. And then here we have a bromide, again, attached to this carbon, and that carbon happens to be attached to 3 carbons. 1, 2, 3, and this is tertiary, so this has to be SN1. Okay, so again, if it's primary, you already know which mechanism it's using. If it's tertiary, you know which methods it's using. If it were methyl, you would know which one it is using. The only time we don't is these. So from here on out, we're only worried about secondary reactions, pretty much, or secondary alkyl halides. All right, in those situations, it helps to understand nucleophiles. So here's kind of a list of some general nucleophiles. Now, in aprotic solvents, which we'll eventually talk about, things get stronger this way. In fact, one really simple method of kind of remembering nucleophile strength is going down this way. On the periodic table, stuff gets stronger. Let me give you an example. On this periodic table, nucleophiles are stronger as they go down this way. Okay? Which means if you're comparing oxygen and nitrogen, nitrogen's going to be a stronger nucleophile. If you're comparing oxygen and sulfur, sulfur is going to be a stronger nucleophile. In fact, anything that has an N, P, or S tend to be much stronger nucleophiles. Given that same information kind of going down on the periodic table here is comparing fluorine, chlorine, bromine, and iodine, but specifically with negative charges, so chloride, fluoride, bromide, and iodide, the stronger one's going to be the one that's lower on the periodic table. Things that are neutrally charged, like these, tend to be weaker. Okay? And things that have negative charges tend to be stronger. So I think I actually make that point in the next page. It says if it has a negative charge, it's going to be a stronger nucleophile than if it doesn't. And it gives you an example of like OH minus versus water. So this one is strong, and this one is weak. Now, it doesn't mean they're always going to be strong and weak. So, for example, one common scenario you'll come across is SH negative versus like H2S. Do you remember that down on the periodic table I said that things with S tend to be strong nucleophiles? This one's a stronger nucleophile, but you'll find on this table, for example, that they're both strong nucleophiles. This one's stronger, but they're both strong nucleophiles. So generally the weak nucleophiles tend to be these main ones right here, where you just have some kind of neutral OH thing, whether it's water, methanol, ethanol, propanol, some kind of all will give you a weaker nucleophile. Okay, so given that, let's see if we can guess if we have a secondary situation. So remember, we're only worried about secondary. You'll never have a primary paired with a weak nucleophile, for example. Okay, so we're only worried about secondary. So we're going to try to figure out which one it's going to react with. And probably it would help if I wrote this very, very clearly. I think I might have on the other page. But SN2 are going to prefer strong nukes. That's because it's a single reaction. It's a single step reaction, right? So it has to be a strong enough nuke to come in and force that leaving group to leave. But an SN1 wants a weaker nucleophile. Okay? So given that, let's go ahead and look at these. This first one has a negative charge. Negative. That means it's going to be strong, which means it's going to occur via SN2. Does this one have a negative charge? No, it's neutral, and not only is it neutral, it's neutral with an oxygen. Oxygen was not one of the ones I circled here as okay to be like neutral. Okay, so oxygen is going to be it's neutral, which means it's weak, which means it'll be SN1. I minus. We already discussed down on the periodic table, I minus, nice strong nuke. This is N, it's negative, strong, so this will be SN2. Anytime you have a strong, it's SN2. Weak is going to be SN1. CN minus. Not only is it negative, but you also have it bound to an N. Okay, so the negative charge is on an N, which means it's extra strong. And this is going to react via SN2. Then we have MEOH. Hopefully you recognize that as a neutral. It's the lone pair happens to be on the oxygen here, and oxygen is not that strong, it's weaker. So put this all together, this reaction would occur via SN1 with this substrate, with the secondary thing. All right, MEO negative. Now all of a sudden we've taken off that H, we've made it a negative charge. Now it is negative. Negative is going to be stronger, and that's going to occur via SN2. Then we get to Cl minus. Now Cl minus is interesting, and I put this here because I want to use it to introduce the next topic. But if we look at these strong nucleophiles, remember we said down the periodic table they get stronger. So this is the increasing strength. Strong. Cl minus is the weaker of all of them. So Cl minus is, even though it's technically a strong nuke, so in this situation it's negative, it's strong, and it will occur via SN2. There could be some questions about it depending on the solvent that you put it in. Because again, it's kind of like right at the top, it's in the middle. And this is where we run into the last issue, the last thing that matters really, and that's the solvent. So we'll go back to those examples in a minute. Okay, so the solvent. So if you have a strong nucleophile, a product solvent will make the SN2 reaction speed up. So we say that the SN2 reaction is favored. So if you have one of these as your solvent, and it'll usually be written like this, like let's say you have and you have that Br, and you're reacting with a strong nucleophile, so let's say OH negative. Okay. You would put that sucker in, let's say, acetone to really put a stamp on it. You already know that this is secondary, so you're not sure, but this is a strong nucleophile. You already know this will occur via SN2, but acetone makes sure it happens. It makes the magic happen. So this will, just in case you're wondering the product, OH. Okay. So this will occur via SN2. Okay. And the same could occur anywhere. So you usually you're gonna put the solvent down here on the bottom underneath the arrow, and then you're gonna put the nucleophile up here. So any of these paired with a strong nucleophile is just a way to put a stamp on it and say, hey, it's definitely going via SN2, right? But when a reaction occurs in polar product solvent, that's pretty much anything that's got hydrogen bonding going on, so something with an NH or an OH, then an SN1 reaction is favored. So here are some examples. The good news is these up here, pretty much anytime you have an acronym or an initialism, I think is actually the correct term of those. Anytime you have something up here, it's going again via SN2. And down here, we'll actually draw them out. I might say water. In fact, I think I did in this, but usually you'll actually have it drawn out, so you know if there's going to be hydrogen bonding. This is pretty much the main case of if we have like an H2 and F, that's still hydrogen bonding, but it's very rarely encountered. Okay, so these will all occur via SN1. Okay. So you will pretty much only question things again when there's a secondary halide. I can't say it enough. So the only time this whole talk is regarding secondary alkyl halides. So first, the nucleophile will help you determine if it's SN2 or SN1, and the solvent just puts a stamp on it to say, yes, it's definitely SN1. So another example, if I took this, like this, and I had bromine, so kind of the exact same thing up here, but I would pair it with a weak nucleophile, like H2O, I could put it in, I don't know, ammonia to put a stamp on it, okay? Or NH3, I'd probably actually just write NH3. And that says, oh, it's definitely occurring via SN1, okay? All right, last but not least, let's do some examples of that solvent. See how we're feeling. Okay, again, the beautiful thing is the solvent usually only puts a stamp on what we already know. So this is strong. It's got a negative charge. This is aprotic, as we should expect, so this is SN2, okay? So the strong and aprotic will go together. This is weak. This is protic, because it's got a hydrogen bonding. This would occur via SN1. Again, we're only talking about secondary stuff, just in case I haven't put a stamp on it enough. All right, here we have a strong nucleophile with I-, and it happens to be, of course, an aprotic solvent. We already know strong would be SN2. That solvent just makes sure we really know it. Cn minus we know is strong. This is aprotic, as we should expect, and it occurs via SN2. Here we've got a weak in ammonia, which I said I would draw out, and I didn't, I lied to you. So NH3. This has an N to an H bond. This is protic. So what do you think it's going to occur via? Hopefully you agree, SN1. All right, and then we have here MEO negative. This is strong. DME is aprotic solvent, as expected, so this is SN2. So in case you haven't seen it, strong goes with aprotic, weak goes with protic, strong, aprotic, weak, protic, strong, aprotic, like they all stick together. Strong goes with aprotic. Weak goes with polar protic. Cool. All right, now we get to this one. Remember how I said that chlorine was kind of in the middle? In fact, you can compare our answers, because I copied the exact same thing. You can compare our answers, and we have the exact same ones from the previous problem, SN2, SN1, SN2, SN2, SN1, SN2. But then we got to chlorine, and we said, meh, it's kind of middle of the road, right? Just looking at the periodic table. So chlorine and water, this would be an example where a protic solvent actually matters, or aprotic. Chlorine, we know, is like medium, okay? So in water, which would be a protic solvent, it's going to occur via SN1. So this is where you're like, I don't know, but the solvent tells us it's SN1. And in this case, we have chloride and we don't know, but it's an aprotic solvent, and that tells us it's got to occur via SN2. All right, crew, let's put this whole thing together, shall we? Okay, so we're just going to do a few examples just to make sure we're good with it. If I look at this, it's tertiary. I need it to look at nothing else. This is tertiary. This is reacting via SN1. Cool. Now to remind you, and in fact, let's just go ahead and do these mechanisms. Let me pull this camera up a little bit. The leaving group leaves. So SN1, the leaving group's going to leave. And that provides us with a positive charge right there, okay? The reason SN1, again, only occurs via secondary or tertiary is because this is only stable. The positive charge is only stable in secondary or tertiary carbons. And now we have that CH3OH. The electrons from that come in and attack that. I should have left a little more room. I'm going to go up here. So that gives us this. And if you remember, either another one of these can come back and grab it, the Cl can come back and grab it, but usually one of these will come back and grab this extra hydrogen to pull that charge off of that thing. Okay, this is not the best example to start with. Maybe I should have just given you the product, but we get OCH3 as our final answer. All right, if there were stereochemistry involved, this would have been a racemic mixture. You'd have an R and an S. Okay, here, this is where you always get the inversion, but there's no stereochemistry involved. Hopefully you agree that that's a primary. The bromine's attached to this carbon. That carbon's attached to just one carbon right here. Back to stay consistent, just in case, because sometimes these are the hardest ones to see for some reason when they're hanging off, because you see this and you think it's secondary, but this carbon is attached to just one carbon, and that's why it's primary. So this will occur via SN2. That is going to go ahead and attack this carbon, and that's going to leave. And you'll have essentially just a substitution with the SH. Okay, now we have this one. Here we have strong. The reason I said strong was because I already saw that this is a secondary alkyl halide. Okay, so remember, secondary, that's when we have to have any kind of questions. Here, we already knew this was going to be SN1 because it was tertiary. Here, we knew it was SN2 because it's primary. Here, we don't know, but we have to look at the next best thing. This is a strong nucleophile. Now, you could have totally paired that with like DMSO or THF or something like that, some kind of aprotic solvent to put a stamp on it if you wanted to. Okay, and we know that all these things are strong and those aprotic solvent will occur via SN2. This will attack, that will go, and you get, with sound effects, so this attacks this, so we have an oxygen here. Sorry, I should probably have done this a little better. Oxygen. Let's see if I can salvage this. Ding, ding. Because then you have an ethyl group there and there. So I could have written OCH2CH3 or just draw the ethyl group. All right, this would have been an inversion product. This one also would have been inversion if there were stereochemistry. There's no stereochemistry currently, but. All right, this next one here, again, we have a secondary. Stick with my purple and my pink. Boom, boom. Notice that the carbon that that's attached to is attached to 2 carbons. So this is secondary, so that's the only time we're like, oh, what's gonna happen? No worries, this is weak. It's neutral oxygen. So you know that the very first step is that leaving group is gonna leave because this is going to be an SN1 reaction. Now, of course, you could have paired it with a polar protic solvent, like water, ammonia, anything with a hydrogen bonding. And you'll get positive charge is your first step. Then we have that methanol. And this electrons are going to go boop, boop, which will give you OCH3. And you'll have an H over here, and that will be positively charged. And then either the leaving group or another H, CH3OH, will come back in and grab that hydrogen. It acts as a base, grabbing this acid, and that will result in your final product of that. So if you get scared about this stuff, I do want you to know the mechanisms. You absolutely do need to know the mechanisms. But if you go back and you look, essentially here we reacted with methanol, so we added an OCH3 to where the chlorine was. Here we reacted with methanol, so we added a OCH3 to where the bromine was. It's the same kind of thing. Okay, now we get to this one. Hopefully you agree. This one's secondary. So secondary, we're like, I don't know, but this is weak. So this is going to definitely occur via an SN1 reaction. SN1 is always going to give you the racemic mixture. So you will get, I'm going to save a little time because it's only asking for the products. You will get an OH there because the water will join and then the water will come back and grab an H+. And you'll get an OH there. Right? So wedge, dash, you'll get the racemic mixture. Again, that's because the bromide left, so it can attack from either direction. Here, though, I have this chlorine's attached to this. This carbon is only attached to one other carbon. So this is definitely primary. This D, by the way, is deuterium. It's just hydrogen with an extra neutron in it. Okay. It acts like hydrogen, but it's a little different, so it allows you to do chiral centers like this. Okay, so it's primary. this has a negative charge, strong, not that it mattered because this is primary. We knew it has to occur via an SN2. And this sucker is going to come in, whoop, and pop that off. The only problem is it has to happen via the backside attack. Okay, it can't come directly at that chloride. It has to go around that chloride. In order to do that, when it does that, it shifts the H and the D around. So we'll get the inversion product. Okay, so it'll be a carbon, triple bond it to a carbon to an H. And so what was on a dash will be on a wedge, and what was on a wedge will be on a dash. So now I'm going to just go ahead and put that hydrogen on a dash, put that deuterium on a wedge. Okay, so make sure you recognize that. We switched these because you got the inversion. All right, crew, I hope that helped. And yeah, sorry it took me so long to get this going, but I think this covered all the problems that students mostly encounter. So, all right, have a great day. Bye.